let's take a look at a more practical use of wave interference. Namely, what happens when waves interfere with a thin film coating another material. Okay? So let's consider this case. We have some incoming wave, let's just think it's in air, and it encounters some film. This film, or coating if you will, is coating some piece of glass. It can be any material, but let's think of glass. And it's very thin, it has some thickness t, little t. Well, if that glass is greater than the film, and the film will be greater than air, then we can track what happens. Well, if the incident wave encounters this this film air boundary, well, it can either reflect or transmit. So let's look at the reflection. Well, the reflection will just simply give it a phase shift of pi. So pi phase shift. Okay, let's call this wave 1. And we can also transmit. So let's look at what happens when this wave transmits. Well, we have a new film refractive index, and we know that in the film, we are going to have a new speed. So new v, it's called a v film. And because we have a new speed in the film, we're going to have a new lambda. This new lambda will be whatever our original lambda was divided by the refractive index of the film. Okay? Remember, lambda changes, but the frequency, which is the fingerprint of the wave, will remain the same. So let's draw that. Let's say our film index makes the wavelength decrease. So let's draw a smaller wavelength wave going into the film. And then it encounters a glass. And then same thing happens. It can either transmit or reflect. We don't care about the transmission. Let's see what the reflection happens. Well, again, it's going to reflect and take a phase shift of pi. So same lambda film. That doesn't change, but we have another pi phase shift because we encountered another boundary with a greater refractive index. So now, once we get back to the original air film boundary, well, now we enter the original refractive index, so we go back to our original lambda. Those two are the same. But we still overall have a pi phase shift because of that glass boundary. So let's call this wave now 2. So these two waves are now the same wavelength, have the same overall pi shift, but wave 2 traveled twice the thickness of the wave, of the film, rather, more than the wave 1. So we know that wave 2 traveled 2t more than wave 1 in the film. Okay? So let's look at how are these two waves now going to interfere in air. So once they get spit back out into the air, well, that interference will depend on its phase shift. Remember, phase shift is k, and this is going to be k of where they traveled. So where the phase difference happened will happen in the film, because that's where we had the shift in distance plus an intrinsic phase shift. But we know that both the waves came from the same source, and they both picked up an overall pi phase. So this will be 0 because they have the same source. So all that matters is that path length difference. And we know that this path length difference, in our case, is 2t. Okay, so let's write down what happens if we put in our 2t. We know k of the film is the wave number of the wave in the film. Well, that's 2 pi over lambda of the film. And our path length difference is 2t. We know that lambda of the film is lambda over the n of the film original. And I'm going to keep that overall 2 pi outside. And we have a 2t n of the film divided by lambda. So what do we have now? We have 2 pi times some number. Well, in constructive interference, we require it to be 2 pi times a number. So we're going to say that this number has to be some integer for constructive. Or, if that number happens to be a half integer radians, then it can be destructive. Okay. So we have a condition that tells us whether, for a given thickness, the lambda that we get is going to be constructive or destructive out here. So let's write down that condition. Okay, so this is what we got for the phase difference of the two waves. And again, we have 2 pi times some number. So if this number is a half integer, is equal to m minus a half, so a half integer, then we get destructive. Or if we have that number be a whole integer, then we have constructive. Okay. And notice how m is your choice. So you can either pick the largest value of m you can think of, in which case we'll give you the smallest possible lambda you can have, or the largest possible thickness you can have. Same thing here. You can pick a large m, which will give you a small lambda, or a large t, or vice versa. Pick a small m, and it will give you a large lambda, or a small